In this video, I'm going to go over the sum and different identities. And first, we're going to look at the sum and difference identities for cosine and sine. Now, for cosine and sine, what these identities are indicating is that we have cosine of two angles. We're labeling these as angle A and angle B. Same thing for sine. And so what is happening is we are either adding two angles or subtracting two angles, and then taking the cosine or the sine of those. And then we have two formulas or a formula for each of these. Now, a common misconception that I want to clear up is that if we have something like cosine, and let's just assign values for A and B. So let's say I have cosine of 30 degrees plus 45 degrees. That is not the same as cosine of 30 degrees plus cosine of 45 degrees. So we don't simply distribute in this way. So that's a common mistake that students sometimes make, so we want to avoid that. What the formula is telling us to do is looking at the cosine, sum and difference. So if I have cosine of A plus B, what I do is I take cosine of A, multiply that by cosine of B, or the second angle. And then what we do, notice that I reverse the operation. So if we are adding over here, we are going to subtract on the right-hand side. And if we are subtracting, or if we're finding a difference, then we add on the right-hand side. So cosine has the opposite or the reverse operator. Sine is the same. Notice if I'm adding over here, I add here. And if I subtract, I'm going to subtract. Okay. The different one thing to note, though, is here I have sine of the first angle times cosine of the second angle, and then sine of the second, cosine of the first. So hopefully this will make a little more sense once we go through these couple examples. The first one says, find the exact value of sine of 165 degrees. Now, thinking about what's on the unit circle, 165 degrees is not one of the normal or one of the angles that we know on the unit circle. So here's 180, and then kind of going out of order, but those are the angles in the second quadrant that we are familiar with. 165 is, right in here. So we don't know the sine value from the unit circle for 165. Now, this is the instance when we want to use the sum and difference identity. We use the sum and difference identity when this angle is not on the unit circle. So what I'm going to do is I'm going to come up with two angles that either add together, or when I subtract them, I get 165, such that the two angles that make up that sum or difference are on the unit circle. Now, two angles that could add together to give me 165, well, 45 degrees and 120. I could do those two angles. Right? Both of those are on the unit circle. When added together, they are 165. Another option, let's say 30 and 135. Right? 30 is down here. We'll do one more, and I'll come up with a difference. Maybe 210 and 45. So 210 minus 45 degrees. 210 is down here. Okay, so all of those are possibilities for the A and the B from the formula. So it doesn't matter which combination we use, and actually there's an infinite number of combinations, but usually we want to pick something in the first revolution around the unit circle. All right, so I'm just going to use this first one. Okay, so this is sine of A plus B, so 45 degrees plus 120 degrees. And then I'm just going to plug in everything from the right-hand side. So I'm going to say sine of the first, sine of A is 45, sine of 45 times cosine of the second. For sine always has the same operator. So this is plus here. And now I'm going to say sine of the second angle, sine of 120, times cosine of 45 degrees. Okay, then I'm just going to go through and fill in the values from the unit circle. One thing that might be helpful is to just find sine and cosine for 45 and 120. I'll fill these in on the circle. So the values at 45 are root 2 over 2, root 2 over 2. For 120, I'm going to have negative 1/2, comma, root 3 over 2. So I can go ahead and fill these in. Sine of 45 degrees is the y coordinate at 45, so root 2 over 2. Cosine of 120 is the x coordinate, so negative 1/2, plus sine of 120 is root 3 over 2. Cosine of 45, root 2 over 2. And then I can just multiply, so I get root 2 times negative 1 is negative root 2 over 4, plus root 6 over 4. And then I can write this as a single fraction, negative root 2 plus root 6. And there we have it. Okay. Now, we could type this into the calculator and get a decimal approximation. And I'll go ahead and do that. Looks like my calculator might be dead. Here we go. All right, negative root 2 plus root 6 divided by 4. And I get about 0.2588. So one thing to notice or remember is that this is the exact value and this is the approximate value. So in the instructions, when it says to find the exact value, we want this one right here. And one last thing to mention is that, remember, the angle 165 is in quadrant 2. Sine in quadrant 2 is positive, right? The x coordinate is negative, the y coordinate is positive. So sine is positive. And this right here is also positive. So that's a check that we can do with our work. We want to make sure that we have the correct sign. The correct sign. In other words, we want to make sure that it's properly positive or negative. All right. Let's look at the next example. We'll go a little quicker on this one. This is saying find the exact value of cosine of pi over 12. Now this is a little bit tougher just because this angle pi over 12 is in radians. So we want two angles that add or subtract to pi over 12 that are on the unit circle. Now this is sometimes tricky because there's no denominators of 12 on the unit circle. But I know that 4 pi over 12 and 3 pi over 12, that subtracts to pi over 12. And if I were to reduce these, I would get pi over 3, pi over 4. Those values are on the unit circle, so I can use these fractions up here. Another way to go about this is to convert pi over 12 into degrees. That's going to be the same thing as cosine of 15 degrees. And if you work with this in degrees, sometimes it's easier because we can easily see that this is cosine of 45 degrees minus cosine of 30 degrees. Or I shouldn't write it that way. It should be, I should write cosine of 45 degrees minus 30 degrees. And we could go about it that way. I'm going to do this one in radians, though, just so we see an example of this in radians. So cosine of pi over 3 minus pi over 4. The identity for the difference of cosine, I'll slide up here. Remember, we're going to reverse the operation. And then I have the cosines first and then the sine. So this will be cosine of pi over 3, cosine of pi over 4. Switch the operator. And then I have sine of pi over 3, sine of pi over 4. And then we just go ahead and fill these in from the unit circle. So cosine of pi over 3, that's root 3 over 2. Cosine of pi over 4 is root 2 over 2, plus Sine of pi over 3 is 1/2. Sine of pi over 4 is root 2 over 2. Multiplying these out, I get root 6 over 4 plus root 2 over 4, combining to a single fraction. I get this. Okay, and again, I could turn that into a decimal. One thing to notice is that pi over 12 is in quadrant 1. Cosine is positive in quadrant 1. This is a positive value, so that's a good... doesn't mean that I'm correct, but if this was negative, I would know that I did something wrong. All right, so we can use these sum and difference identities to verify other identities. So let's see what we have here. I have cosine of x minus 3 pi over 2 is equal to negative sine of x. So I want to show that these are equal to each other. I'm going to work with the left-hand side here. And this is just cosine of a minus b here, right? I have a and b. So I can expand this using the difference formula. So that'll be cosine of x times cosine of 3 pi over 2. Switch the operator. I have sine of x, sine of 3 pi over 2. And I want to show that that's equal to negative sine of x. Now, cosine of 3 pi over 2, that's equal to 0. So this whole thing, that whole term becomes 0. Then on the right-hand side, sine of 3 pi over 2 is equal to negative 1. So what we get is negative sine of x. So I have this verified. Okay. Another application of the sum and difference formulas is the cofunction identities. We've already seen the cofunction identities. Remember, sine of theta is the same thing as cosine of 90 degrees minus theta. Okay, and on all of these, I could swap in 90 degrees for pi over 2. Those are equivalent. So we say that cosine and sine are cofunctions of each other. Tangent and cotangent are cofunctions of each other. And again, I'm just writing degrees, but I could swap out all of these 90 degrees with pi over 2. And then secant and cosecant are cofunctions with each other. Okay, so one way to verify these, well, we did this in a different video. We verified these using a right triangle and showing that the sum of the angles in a right triangle all add up to 180. Once we take out the 90 degrees for the right angle, we're left with 90 minus whatever angle is left. So that's kind of how we verified these previously. Another way to do that, though, is just using the sum and difference formulas. So I'll do this for sine. Sine of 90 degrees minus theta. Let's show that that is equal to cosine of theta. So I'm going to say that this is A, this is B. Sine, the difference formula for sine, I have sine of the first times cosine of the second. I keep the operator the same, so it's subtraction here, so I'm going to subtract here. And then cosine of 90 degrees, then sine of theta. So sine of 90 degrees is 1 times cosine of theta minus cosine of 90 degrees is 0 times sine of theta. So this whole term goes to 0, and we are left with cosine of theta. So that shows this cofunction identity up here. And we could do that for all of these. We've already seen the sum and difference for sine and cosine, but we're going to look at tangent and cotangent here, or really tangent, because if we have sine, cosine, and tangent, we can get the reciprocal identities just by taking the reciprocal. All right, one last identity to verify here. So notice on the left-hand side, I have cosine of x plus y, so I'm going to expand that. That'll be cosine of x, cosine of y, minus sine of x, sine of y, divided by, in the denominator, I'm going to just keep that the same, cosine x, cosine y. And I'm not going to do anything on the right-hand side just yet. Let's see where this left side leads me. So I'm going to split these two fractions, because what I notice is that first term in the numerator is the same as the denominator. So that first fraction is going to become a 1. Okay, so this is equal to 1. So I have a 1 minus, and then I have sine of x cosine x. Sine over cosine is tangent, so that's just tangent of x. And then sine of y, cosine y is just tangent of y. That's a little sloppy. Let's try that again. And that is exactly what's on the right-hand side. So this one, just by using that identity in that first step, that gets it to us. All right, and then a couple last things in this video. Let's look at the sum and difference formula for tangent. Now, I'm not going to derive this, but you could do that, and I'll mention how here in a second. So the sum and difference formula for tangent, I do tangent of A, or tangent of the first angle. I keep the operator the same in the numerator, and then we have 1, and then in the denominator I reverse the sign, or the operator. Try not to say sine, because sine means something different in trig. So notice that this is reversed and this is the same. Okay, and the way that we verify this is remembering that sine is the same that tangent is the same thing as sine over cosine. So if I have tangent of A plus B, that's the same as sine of A plus B over cosine, right? Tangent is sine over cosine. Okay, so if we were to expand these out, some things would cancel and we would end up with this tangent. So that's where this is coming from, but again, I'm not gonna show that here in this video. There are a lot of videos of that, I'm sure, on YouTube already. Okay, and then lastly, let's look at this example. Find the exact value of tangent of 17 pi over 12. So again, we want to find two angles. Well, first of all, we need to notice that 17 pi over 12 is not a value on the unit circle. And so we must find two angles that add together to give me 17 pi over 12. And those are one option is 8 pi over 12 plus 9 pi over 12. And if I reduce those, I get 2/3 pi plus 3/4 pi. And those values are in the unit circle. So that's what I'm going to use. So I'm going to say tangent of 8 pi over 12 plus 9 pi over 12. That is equal to 17 pi over 12. I'm going to rewrite this with the familiar angles from the unit circle. Okay, and just like we did previously with I think it was a cosine example, where we had the angle in radians, you could have also converted this angle into degrees. And I don't know what that is off the top of my head. Maybe 270, 255, I think. Don't be mad if that's not right, but I think that's the angle in degrees. So you could have split that up into two angles that add up to 255 as well. Okay, so expanding this out, I'm just going to use that formula from above. So tangent of 2 pi over 3. I keep the sign or the operator the same in the numerator, tan of 3 pi over 4. And then in the denominator, we're going to say 1. I reversed the operator, so now it's minus. Oh, I made a mistake. I don't know if I said this, but up here, this needs to be A right there. Okay, so back down to our example, I'm going to have 1 minus tangent of 2 pi over 3 times tangent of 3 pi over 4. So let's find these values for tangent on the unit circle. 2 pi over 3 is up here, and those coordinates are -1/2 root 3 over 2. So tangent of 2 pi over 3 is equal to y over x, so root 3 over 2 divided by -1 over 2. 2's cancel, I get -√3. So tangent of 2 pi over 3 is -√3. And then 3 pi over 4 is in this right here. And that's -√2 over 2, root 2 over 2. So tangent at 3 pi over 4 is y over x, root 2 over 2 divided by -√2 over 2. That's just -1. So those are the values I'm going to use in this fraction. So tangent of 2 pi over 3 is -√3. Tangent of 3 pi over 4 is -1, divided by 1 minus tangent of 2 pi over 3, -√3. Tangent of 3 pi over 4, -1. Simplifying this, get -√3 minus 1 in the numerator. In the denominator, I'm going to have 1 minus, and then these are both negatives, so that becomes a positive. So 1 minus a positive root 3. And we can leave our answer like that. We can do some other fancy things to get rid of the radical in the denominator, but that is an okay answer for our purposes.